So the reason why we study standing wave is because standing wave is another way to classify our waves. Okay, so behind me there are two types of wave, and they look kind of the same wave drawing, but this is not until I press the play button, and then you realize that the one that you see on the right, is kind of familiar, right? What we are looking at is actually two wave particles, okay? And then we are comparing their phase relationship, and this is what we call anti-phase because they are always moving in the opposite direction. Now let's check out the one in red, okay? So the one in red is, maybe I'll just pull this here, okay? So the one in red is actually a stationary wave. So it's not as kind of fast, but then you realize that particle A and B also always opposite direction, right? So for both waves, the particles are always in opposite direction. But let's pause for a bit. Just going to pause here. And I want to change the position of particles A and B. Let's say particle A and B is somewhere like this. Okay, I'm just going to roughly put them on two sides of the same mountain. Then this is where it gets very trippy. Because if I look at this one, the one on the left, you will realize that particle A is moving up, particle B is moving up, but sometimes, if I pause here, they are moving in the opposite direction. Okay, but if you look at this, the red color wave, the stationary wave, you realize that A and B still same direction. Yeah. So in this video, we actually need to compare all of these things. We actually are going to compare what is the difference between this stationary wave, which is a new kind of movement, okay, wave motion, compared to what we're familiar with, which is the good old energy wave. Okay, so the first thing I realized, let's say for example, if you don't look at the particle, is that the wave profile of this wave, this is a progressive wave. And you can see, right, let's say I take a few pictures of this gray color progressive wave. Maybe I take a picture here. So we're going to pause this one first. Maybe I take a picture here, and then I take a picture here, and then I take a picture here, and then I take a picture here. This gray color wave is moving, but this red color wave is stuck in place. It's moving up and down, but it's moving up and down in place. Okay, so we're going to compare this, and we're going to draw that in a table. Okay, so again, waves can be classified into transverse or longitudinal. That's the first classification you learned in the previous chapter. And this part, we are going to look at the second classification, which is progressive versus stationary or standing waves. So let's look at progressive waves. On one side, we know that the progressive waves wave profile will shift. Okay, so I'm going to draw those snapshot pictures that I told you just now. So this is an example. The wave profile, not drawn perfectly, will shift from one side to the other side. Okay, this is a better drawing. You can see the wave profile is moving. Okay, so the first thing I can describe is the wave profile. So I will say that the wave profile and energy travels from one point to another. This is our regular, good old progressive wave. So the key thing about progressive wave is there is transfer of energy, or there is a movement of energy from one point to the other. Okay, so the wave profile will travel, the energy will travel. What about stationary wave? Remember, all the waves are trapped. When we look at this one, you can see that the particles are sort of like trapped. So if let's say I pause here, I draw this picture, then I draw this picture, then I draw this picture, then I draw this one, then I draw this one, then I draw this one, then I draw this one. I sort of like have these things stuck in loops, right? So imagine if I keep drawing this all on the same picture, I'll probably get something like this. Okay, after some tablet difficulties, this is it. Maybe I'll just draw a small number lah. Okay, this is position number 1, position number 2, position number 3, position number 4, position number 5. So the wave profile will go from 1 to 2 to 3 to 4 to 5. And then it will go back. Okay? It's really hard to draw a drawing on a piece of picture when actually what concerns us is the movement. This is what we're drawing. Okay? So please understand that the wave profile is stuck in place. All right, so visualize and understand that these two really different movements. One actually travels, and the other one just moves up and down in the same place. Okay, so in this case, we will say that the wave profile appears to stay in place. If the wave profile appears to not move, just boing, 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 just stuck at the same position, your energy, right, is also stuck, lor. The energy is here, just like, yo, dude, we can't go. There's no traveling in energy. The energy is trapped. Like the particles are only moving up and down. The energy is not being moved. RIP. Okay, so we'll say wave profile appears to stay in place and energy is trapped between nodes, because don't forget, we actually name these important points in this one. These are nodes. Here is another node. This is a node. And finally, this is also a node. So the energy is trapped between two nodes. Particles is going to vibrate a lot, especially at the antinode here, but the energy cannot transfer from one point to another point. Hence, stationary wave. Okay, so energy is trapped. Maybe I use a different color for this. E. All right. So this is the main difference between progressive and stationary wave. But now we need to level up a bit, okay? So let's compare the amplitude of the wave particles. All right? We want to look at, do all wave particles have the same amplitude or a different amplitude? Okay, so now we're back at this one again. And I want you to look carefully first at the first drawing, which is the gray color progressive wave. For this progressive wave, you realize that the highest position of particle A is here, and it will be the same as the highest position of particle B, because amplitude is the distance measured from the equilibrium position to the highest point of particle B, or lowest point. Okay, so the distance, the maximum distance achieved by particle B looks the same as the maximum distance achieved by particle A. Just, not at the same time. So particle A here, now it's particle A's time to have maximum displacement. And then after that, it's particle B's turn here. Now it's particles B turn to have maximum displacement. So the amplitude of all of these particles is the same. It's just that they don't reach their peak at the same time. That would be your progressive wave. Teacher, what about this one? Well, this one moves a bit fast, but never mind. Maybe I'll put a particle here, and then I'll put a particle here. Now this one is where things get a bit strange, because you realize that particle A, the amplitude like very small like that, only move here, it moves in a small little inch. But particle B is very hyper. Look at it go, man. It goes very low, it goes very high compared to particle A. So for stationary wave, you realize that because this simulation tells us where the particle's amplitude is, at the same time. So you realize that if particle B is at antinode, the amplitude is the greatest. It goes to the highest position, it goes to the lowest position. And particle A, the amplitude is kind of small. And in fact, perfection. And in fact, if let's say I move particle A to a node like here, magic, particle A's amplitude is what? What do you think is particle A's amplitude? Is particle A moving? No, it's not moving. I gotta move it. Particle A is like, no, bro, I'm gonna stay here. I'm a node. I don't move. No, say no to moving, says the note. So particle B is like, yo bro, you want to play? You want to go out? You want to have fun? Look at particle B. Particle A is like, nah, I'm just going to chill here. So the amplitude between A and B is so different. It will be 0 if, let's say, particle A is positioned at a node, and maximum if particle A is positioned at an antinode. So once again, progressive wave, amplitude the same. And for stationary wave, the amplitude is different unless these two particles just happen to be here. Okay? Let's say, for example, an antinode and another antinode. But Miss, what about just now like that? You know, you put one particle here, then you put another particle here. It's a bit like, you know, if I draw a horizontal line, they're at the same place. Okay? Sure, these two particles will have the same amplitude. Meaning within two nodes, there will be two particles with the same amplitude. Otherwise, everyone else is different. Let's write that down in the sentence. So the amplitude of wave particles for progressive wave is constant for all wave particles, but you can add a note here. It reach maximum displacement or reach amplitude at different time. But for standing wave or stationary wave, the amplitude will change from node to this point here is an antinode. Antinode right in the middle, this is antinode. So it varies from 0 at the node to maximum at the antinode. So the sentence that we're going to use to describe is, if I look at the displacement of the particle, it will be 0 here to maximum. Look at the green color particle I'm dragging to minimum. Okay, so if I play, particle B is not going to move, and then particle B will begin to move more as I travel, or if I drag the particle. Okay, kind of hard, but if let's say if I drag the particle here, the amplitude increase. So 0, amplitude increase to maximum here. If you want to draw this here, you can see that, let me use orange for this. The amplitude here, so I'm just going to write, you see, very dangerous, or if I don't write amplitude and I write A, then A is for antinode. Okay, so the amplitude here is 0, and then the amplitude here, let's say for example at this position, here to here is the amplitude. So amplitude, maybe I will use small a1. So this one is a1. Okay, the height of this arrow. But if let's say you reach here, this is your amplitude a2. Let's say you reach here, this is your amplitude a3. Yeah, whoops, accident delete. Okay, if you reach here, this is your amplitude a4. So you can see the length of the orange arrow become longer and longer and longer from node to antinode to shorter and shorter from antinode back to node. This is A5. So this is what this sentence means. Varies from 0 at this, node, back to maximum. So this A3 is maximum, okay? Then back to 0 again at this node. But the interesting thing about this standing wave, see if I can zoom in a bit so you can see, is that it doesn't really matter where I put the particle. Yeah, let's say I put like that. Okay? And they actually reach maximum at the same time. Okay? So look at this. They both peak. They both reach the highest position together and the lowest position together. Okay? Because the highest position, the lowest position is something like this. Oops, a bit hard to pause, but if you stare at this right now, this is the lowest position. They reach this at the same time. Okay, so this is a direct opposite of the amplitude of the progressive wave, right? So progressive wave, they have the same amplitude, they reach at different time. Standing wave, they have different amplitude, but they reach at the same time. Let's write that down. So reach maximum displacements at the same time. All right. So much movement. Of course, we need to use the term phase relationship, phase angle. Okay. So for progressive wave, it's pretty straightforward. If I check out a progressive wave like this one, most of the time if I randomly plop two particles, I don't know lah, like that lah, they are not in phase one, sometimes opposite direction, sometimes same direction. So adjacent particles are basically out of phase or not in phase. Okay, so any two adjacent wave particles are out of phase or not in phase. But standing wave, chef kiss, so perfect. Okay, I'll show you. Maybe I make this bigger. Hang on. Okay, so if you look at this standing wave, and if I play this, you realize that they always move together. Did you really? Yeah lah. It doesn't matter where A and B is. You can put them in some random spot like this. They move up together, down together, up together, down together. Don't need 181. Not necessary. As long as they are in between, look at my cursor, this node and this node, they move together now all the time. Good life, good life. So any two particles, doesn't really matter where the particles are. Maybe now this one I put here, now this one I put, I don't care lah. They always move together. Hence the word standing wave, because everything between two nodes will travel together. Okay, so let's write that down. I'm going to say any particles between two consecutive nodes travel together. So they have the phase angle of, yes, I heard you, my favorite number, 0. So all particles between two adjacent nodes. Let me add the word adjacent. Okay, so all particles, not just two, any particles between two adjacent nodes are in phase. Okay, so that's why it's important for us to know where the nodes are. All right, so instead of scrolling up and down, maybe I'll just do a quick sketch of a standing wave here. So this will be one position of the standing wave. This will be the second position of the standing wave. So this is like a budget version of this drawing now, okay? Ain't nobody got time to draw something so colorful, so butterfly, okay? Budget version. But the important thing is to identify where the nodes are. So maybe I'll draw another loop for us. Okay, here's another loop in our budget standing wave. Okay, so I'll mark down the nodes, right? So this is your node, this is your node. It means that any particle from here to here is, of course, you can say, teacher, there's infinite particles I can fit. Yeah lah, that one I know. But any particle from here to here, the phase angle is 0. Okay? And then you realize that because of this, the way this wave moves, right, all the particles from here to here, phase angle also 0 leh. But that one, don't write sentence lah. If you can visualize this, it's kind of obvious. Okay? So if you check out this loop, okay, and check out this loop, not the neighbor one, the next one like this one, you realize that this particle AB also in phase or move together all the time. Okay? So it's like alternately in phase and out of phase. Okay, so it can be this and this loop also. If you want out of phase, opposite direction, then it has to be the neighbor loop, like here. Like that is opposite direction. Okay, so again, if you're confused, check out where the nodes are. Between particle A and B, if there is no nodes, you see, particle A and B, or in between them got no node, then this one is in phase. Because they're in between two nodes. That's why they are in the same loop. Okay? But if between particle A and B, let's say I put particle B here, there's a node here. I put I here. See, there's this node here. You see this node here? Okay? Then they are out of phase. See? So if in between them there is a node, there's a node, in between got a node, then out of phase law. In between no node, then in phase law. But if in between them have one node, two nodes, then we back now in phase. Okay? Anywhere, man, in phase. Okay, so any point from where my cursor is tracing is in phase if you take two of them and compare. Okay, so it's about how many nodes are there in between you. If there are no nodes, look at the arrow, in phase. If there's one node, look at the arrow, opposite direction, anti-phase. If there is two nodes, we're back to in phase. One node, two node. Okay, so something like that lah. We will mark down the nodes. So any particles along the pink color shading, the phase angle is 0. Okay, so since we are comparing, so we're taking a particle from here, compare this one. Okay, so maybe particle A is here, particle A and B. So maybe I'll take particle A and particle B here. Okay, or I can even take particle A and particle C. Okay, say, or B and C also can. Comparing. Okay, so between two adjacent nodes are in phase, between, I guess, three nodes are also, between two nodes are also in phase. Okay, so it can be between here and here. If there are no nodes in between A and B, in phase. If there are two nodes between B and C, also in phase. All right, so what about antiphase? So if you want antiphase, then we need the particles to be along the neighbor loop, or the neighboring loop. So I highlighted the neighboring loop as yellow. Okay, and I will say that this is all particles to the next adjacent node. There are many ways to describe the points, okay, and normally this kind of question comes in objective. So as long as you can visualize it, you need to be able to judge that statement based on the objective points. Okay, so all particles to the next adjacent node is out of phase. We're talking about phase angle of 180. So that would be any particle on the pink loop to the next adjacent node. So when is the next adjacent node? This one, no? Okay, that's why they are in between them, there is one node. So maybe we're comparing this and any point from here. This is kind of a popular objective question. Okay, so I'm gonna maybe plot some particles here just to give you an idea or some example. Maybe instead of A and B and C, maybe you can take a point here, it's P. So for example, the particle B and the particle P. Can be A and P, can be C and P, also can, as long as it's opposite loop. Okay, next particles to the next adjacent node. So read the objective question or the statement given and evaluate accordingly based on the mental image of this thing. Okay, like these two go down together, then the opposite two come up together to feel the standing wave in your heart. Okay, anyway, finally, wavelength for progressive wave is a revision of last chapter, lambda. This is the distance between two particles that are traveling in phase. Okay, so that's lambda, distance between two wave particles that are traveling in phase. I'm pretty sure if I draw a wave profile, for example, like this, finding lambda should be fairly easy for you, because maybe this particle and this particle are traveling in phase. Okay, of course, it will be easier for you if I were to mark down the equilibrium position. Okay, like BRB, hang on, like that. Maybe this one is not that accurate. Okay, something like this. Tablet is struggling. So here to here is lambda. I can take any 2 points as long as they are in phase. What about this standing wave? Well, the good news is because the wave looping is so fixed, okay? So if you want to find lambda, you can just take this node. Let me pause. This node to this node looks like half lambda. Let me draw that down for you. Okay, so here to here, look at the shape, is lambda over 2. And here to here is another lambda over 2. So basically, if I measure node to the next node, nn is lambda over 2. Teacher, not fair, you never label the antinode. Okay, I label the antinode now. Antinode is peak, hyper, peak movement. So here is an antinode. In the middle here, also an antinode. So here to here will be lambda over 2 as well. In fact, there's another antinode here, which is also, when measuring wavelength, lambda over 2. So if you want to find lambda, it's the distance between two adjacent nodes, nn, or the distance between two adjacent antinodes, also lambda over 2. So this AA is the distance between two adjacent antinodes. Okay, just like NN is the distance between two adjacent nodes. So, and then if you're a bit more perceptive, you realize that actually I can also measure from A to N. If you do so, that will be lambda over 4. Okay, so lambda 4 will be an antinode to the adjacent node. All right, this is still sinusoidal. So if you want an entire wavelength, I have to travel from here all the way to here, right? Because that will look something like one complete cycle. Okay, so this is one wavelength. Or we can use the nodes. Between node and another node, here to here, lambda over 2. Between antinode and antinode, lambda over 2. Okay, between antinode to node, lambda over 4. After that, you just count lah. You can count. Like for example, this whole thing, the length of this whole wave, I'm going to draw this out. No, I got space. Here all the way to here. This distance is, okay, see, from this node to this node, lambda over 2. This node to this node, 2 lambda over 2. This node to the next node, 3 lambda over 2. Or we can also call it 1.5 lambda lah, but 3 lambda over 2 lah, okay? So this is the important thing about stationary wave. If you download and you really understand how it moves, then okay already, you're not scared. I can draw how many loops I want to draw. You just start counting lah. This is a counting topic, okay? But if you don't know, then you panic, okay? So we compared different parts of the stationary wave and progressive wave because they are two different classifications. And in the next few videos, we are now going to look at how does this look like in real life, okay? And how do we draw these wave particles, okay? But in the meantime, remember that these two things are very different. And also know that we use this as a case study to learn how to find lambda from a stationary wave, talk about the phase difference for a stationary wave, and also understand that the energy is trapped in between the nodes of a stationary wave. That's all for this comparison, and I'll see you in the next one. Bye-bye.